Ever think about, like, how the universe works on the, like, smallest level? It's seriously mind-boggling stuff. We're talking atoms, particles, the whole, the realm where the normal rules of physics, they just don't work.
A whole different ball game down there.
It's wild. And that's where quantum mechanics comes in. And you're in luck because you sent over Feynman's lectures on physics, right? Specifically, chapter 37 on quantum behavior. So that's what this deep dive is all about.
Feynman, he was amazing, you know. He could take the most complex ideas and make them, I don't know, understandable, fun even.
He really had a knack for it. And one of the things he does so well is, like, these thought experiments, just to wrap your head around these ideas that seem impossible.
Totally. It's like in physics, we say, okay, let's just go with this, follow it through to the extreme, even if it seems crazy.
Exactly. And see where it takes us. So let's try one right now. Imagine a wall, 2 holes in it. Okay? We're going to shoot things at this wall, see what happens on the other side. First up, bullets.
A classic.
Totally. So we fire a bunch of bullets at this wall. What do we expect to see on the other side, behind those holes?
All right, well, bullets, they're particles, right? So each one is going to go through one hole or the other. And if we're looking at where they hit, we'd see most of them clustered right behind the holes. Fewer and fewer the further out you go.
Makes sense.
It's like a bell curve kind of thing.
Right. And here's a key point. The chance of a bullet going through one hole, plus the chance of it going through the other, that equals the total probability of, it hitting the backstop. We're just adding things up. Straightforward.
It's basic physics. But what if, instead of these bullets, we use something that's, more like a wave, like water, for example?
Okay, I like where you're going with this. So picture it. Waves rolling toward our 2-holed wall. What happens as they pass through?
Now things get a little more interesting. Unlike bullets, waves don't just travel in straight lines, right? They pass through those holes and they spread out. They create these new wavelets from each hole. And here's the thing. Those wavelets, they start to interfere with each other.
Interfere, meaning, what, like they're throwing a little wave party on the other side?
Kind of. So in some spots, the crests of those waves, they overlap. So you get a wave that's even bigger. That's what we call constructive interference.
So it's like they're joining forces.
Exactly. But then in other places, the crest of one wave, it lines up with the trough, the low point of another wave, and they cancel each other out. Destructive interference.
Okay.
So you end up with areas where there's basically no wave action at all.
Got it. So on the backstop, instead of that smooth distribution like we had with the bullets, we'd see this pattern, right?
Exactly.
Alternating high points, low points.
The interference pattern, yeah.
Exactly.
Okay. Now, the million-dollar question. What happens if we fire something much, much smaller at these holes? Like an electron.
Now we're diving into the quantum realm.
Right. And if we were thinking like classical physicists, we think electrons. Those are like tiny bullets, right?
It makes sense to think that way.
They're particles. We picture them as these little spheres, zipping around.
Right. But nature has a funny way of proving us wrong, because when we actually do this experiment, I mean, not with this exact setup, but something similar, we don't get that bullet-like distribution. What we see is the interference pattern.
It's wild. It's like those electrons, even though they hit the detector as individual particles,
Right.
they're somehow going through both holes at the same time, just like the water waves.
So they're acting like waves, but they're also particles. This is what wave-particle duality is all about.
That's it. Electrons, and actually all quantum particles, they don't fit neatly into our everyday categories. They're not just a particle, not just a wave. It's like they're both at the same time. At least until we try to measure them, that is.
Okay, my mind is already starting to bend a little bit here. And it sounds like it's about to get even weirder.
Oh, we're just getting started. What if we tried to actually see which hole the electron goes through?
Like catch it in the act. Okay, now I'm really interested. So we're picturing this electron acting like it's in 2 places at once, going through both holes. And we want to like catch it in the act, like which path does it actually take? But how do we even see an electron? It's not like we can just use a magnifying glass.
You're right. It's not that simple. But we can use light. Imagine we put a light source behind our wall with the 2 holes.
Okay.
Now, if an electron passes by, the light might bounce off of it, and we could detect that.
Like a tiny electron spotlight.
Exactly.
Okay. So we set up our detector, we run the experiment again, shining our light on these sneaky electrons. What happens?
This is where it gets really weird. When we try to observe which hole the electron goes through, the interference pattern,
Yeah.
it disappears.
Wait, what? Seriously.
Gone. Just like that.
Hmm.
And what we see instead looks more like our bullet experiment, with the electrons hitting the backstop in a more localized pattern.
So it's like the electrons know we're watching, and they decide to act differently.
It's tempting to think that way, isn't it?
Mm.
But it's not that they're consciously changing their behavior. It's that the very act of observing them, interacting with them, it changes the outcome.
Okay, I think I'm going to need a little bit more of an explanation than it's quantum physics.
Of course, of course. So to see the electron, we have to bounce something off of it, right? Like a photon of light. And photons, even though they have no mass, they do carry energy, they have momentum. It's like, imagine these tiny little billiard balls of light.
Right, like we talked about with light, it's not just a wave, it's also a particle, the photon.
Exactly. And so when a photon hits an electron, it gives it this little kick. And that kick, it changes the electron's momentum, which in turn changes its trajectory.
So by trying to observe the electron, we're actually knocking it off course. We're disrupting its wave-like behavior.
Perfect analogy. It's like, trying to listen to someone whispering a secret, but you keep shaking them while they're talking. You're not going to hear what they're saying. And that, in a nutshell, is Heisenberg's uncertainty principle. It says that there's this fundamental limit to how precisely we can know both the position and the momentum of a particle at the same time. And it's not just a limit of our instruments, it's a fundamental fuzziness built into the fabric of reality at that level.
Okay, so the uncertainty principle, that's a pretty big deal then.
It really is.
But what if we try to be a little gentler in our observation? Like use a dimmer light. That way the photons, they'd be weaker, right? Maybe they wouldn't disturb the electrons as much.
That's a clever idea, trying to be less intrusive. But there's a catch. Light itself, remember, it's quantized. That means it comes in these discrete packets of energy, those photons.
Right, like little atoms of light.
Exactly. We can't make a photon just smaller or less energetic. When we dim the light, all we're doing is reducing the number of photons. We're not actually changing their individual impact. So some electrons, yeah, they'll slip through undetected, but the ones we do see, they're still getting affected.
So dimming the light just changes how many electrons we see, not how they behave when we see them.
Exactly.
Okay. What if, instead of dimming the light, we use a different kind of light? Something with a longer wavelength. Like instead of blue light, we use red light.
Now you're thinking like a physicist. Longer wavelength light does carry less energy per photon, that's true.
So less of a kick to our electron.
Exactly. But we run into a different problem, what's called the diffraction limit. Remember how waves spread out after they go through a narrow opening? Think about those ripples in the water.
Yeah, like with the interference pattern.
Right. And the longer the wavelength of the light, the more it spreads out. So if we use light with a wavelength that's too long, those waves, they become so spread out that we can no longer tell which hole the electron went through. It's like trying to take a picture of something really tiny with a big blurry camera. You're just not going to get a clear image.
So it's like we're stuck. We need short wavelengths to see the electron clearly, but that means high-energy photons, which messes with its momentum. But if we use long wavelengths to try to avoid disturbing it, we can't tell which hole it went through.
It's a trade-off, and that brings us right back to the uncertainty principle. The more we try to pin down the electron's position, the less we know about its momentum, and vice versa.
So it's not just our measurement tools. There's a fundamental limit on what we can actually know about the electron itself.
Exactly, and it really makes us rethink that classical view of the world where we assume if we just measure carefully enough, we can know everything about an object.
It's almost like at this quantum scale, just looking at something, observing it, it becomes a part of the thing itself.
That's a really interesting way to put it, and it leads us to some even deeper questions about what reality really is. But maybe that's a conversation for another deep dive.
Okay, so let me see if I'm getting this. We're not saying there's some deeper level where like the electron actually knows which path it's taking. It's more like at that quantum level, it doesn't even have a definite path until we actually measure it.
You got it.
It's just this like fuzzy cloud of possibilities.
That's one of the wildest things about quantum mechanics, really. We have to kind of let go of certainty and embrace probability, at least at that subatomic level.
So instead of saying the electron is here and it has this momentum, we're saying, well, there's this chance of finding it here with this momentum and another chance of finding it there with that momentum.
Yeah.
It's all about the odds.
Exactly. We can't predict what any individual electron is going to do with like perfect accuracy, but we can figure out the probabilities of different outcomes. It's kind of like rolling a die, right? You can't say for sure which number will come up, but you know there's a 1 in 6 chance for each one.
Okay, yeah, that makes a weird kind of sense. But here's what I don't get. If everything at its most basic level, atoms, electrons, the whole, works, if it all follows these kind of, like, fuzzy quantum rules, why doesn't our world, the world we see around us, why doesn't it look fuzzy and uncertain? Yeah, things seem pretty solid and predictable at our level.
Well, that's the beauty of it. See, the quantum world, it is probabilistic, but as you move to larger and larger scales, from atoms to molecules to, baseballs and planets, those quantum effects, they become less and less noticeable.
So it's like all those tiny quantum probabilities, they just sort of average out. And
Yeah.
that's what makes things seem more, I don't know, concrete in the macroscopic world.
Exactly. It's like if you flip a coin a few times, you might get a bunch of heads in a row or tails. Seems kind of random. But flip that coin 1,000 times, you're going to get pretty close to a 50-50 split.
So the quantum rules, they don't just stop working when things get bigger. It's that their effects are so small, we just don't see them.
Right. Our everyday experiences, they're just too big and clumsy, you could say, to pick up on that quantum fuzziness.
So it's like our bullet experiment. Those bullets, they have a wave nature too, but those wavelengths are so tiny, and the bullets and the holes are so big that any interference effects, they just get completely washed out.
Right.
Classical physics, it works fine for describing how bullets move, but it's really just an approximation, a simplification of this deeper quantum reality that's going on underneath.
Exactly.
Wow, that's really kind of mind-blowing. It's like looking at the world through a completely different lens. The things that seem so familiar
Mm.
are actually incredibly strange and mysterious,
It makes you appreciate the mystery of it all.
which, maybe that's a good thing. Keeps things interesting, right?
Absolutely. It reminds us to stay curious, to keep asking those big questions about how things work, even if the answers just lead to even more questions.
Couldn't have said it better myself.
Mhm.
And on that note, we've reached the end of our deep dive into the quantum realm. We hope you enjoyed the ride
It's been a fascinating journey.
and maybe learned a thing or two about the amazing and, let's face it, often confusing world of quantum mechanics.
And listeners, the next time you look at, well, anything really, remember there's way more going on than what you see. A whole universe of possibilities hidden right there in plain sight.
So until next time, stay curious, keep exploring, and don't be afraid to ask those big mind-bending questions.